I've been talking about SPI a lot lately because that's the protocol I'm using to control the video card. And the next few videos are going to talk about SPI a lot too, as I get the 65 SPI CPLD working, and there'll be some videos on that in the future. In the meantime, though, I thought what I'd do is make a quick video just to show how SPI works for anybody who's unfamiliar with it. So SPI is the serial peripheral interface, a serial protocol for accessing peripheral devices. It's sort of a little like USB in some ways, although it's not nearly as fast or as complicated as USB. It was originally developed by Motorola, and it's used now by a bunch of microcontroller systems, and so it's especially used for microcontrollers talking to sensors. But there's a huge range of SPI devices available: network interfaces, all sorts of sensors, storage, and other I/O devices. So it's a pretty versatile way to get a 6502 to talk to the world. And I use it in two devices: my video card, so this is the connection to the video card, as you've seen, and the compact flash, or sorry, the micro SD card over there. That's an SPI device as well. In its most common configuration, there are 4 signals for an SPI device: 3 shared lines called clock, MOSI, and MISO, and 1 individual line for each device, the chip select. MOSI and MISO are the data transfer lines. Let's pretend that MOSI stands for microcomputer out serial in, and MISO for microprocessor in serial out. Those aren't the real names, but that's what I'll use here. So those are the data transmission lines in each direction to and from the computer. The actual transfer of data is controlled by the clock signal, with 1 bit of data transferred in each direction per clock tick. The clock is supplied by the microprocessor, so that's what determines the speed of the transfer. Chip select, as you probably imagine, works pretty much like chip select does on my main board for my various devices. That is, the chip select signals which of potentially multiple SPI devices will be activated for each transfer. So if there's multiple devices connected to clock, MOSI, and MISO as bus signals, the chip select will set any one of the devices connected to the bus at a time to be the target, so that the devices know when they are being addressed. SPI has multiple different modes, and each mode uses a different signaling arrangement. The devices that I use, my video card and the SD card, both use mode 0. And in mode 0, the clock signal idles low, and the transfer happens on the rising edge of the clock. Other modes have the clock idle high, or have transfers happening on the falling edge. And you can see here, this timing diagram is taken from Wikipedia, and it shows how these 2 parameters play in the different kinds of modes. But my software just supports mode 0 because that's all I've needed for my devices. So I've got my oscilloscope turned on now, which has a rather noisy fan, but hopefully that doesn't interfere with the audio too much. So I drive SPI for my video card for both of them, from parallel ports provided on the 6522s. So there are 2 6522s here. This one uses 1 port to drive the SD card. This one uses 1 port to drive the video card. When we look at the software, I'll talk a little about how I map signals onto different parts of the interface. Although SPI can be a shared bus, I have them running through different ports, although once the 65 SPI is up and running, that might not be the case. And I have the reset signal mixed in there as well. So in addition to the 4 regular channels of SPI, I'm also driving the reset signal for these devices. I think I'm going to change that round. I think for both of them, just connecting them to the system reset will work just fine. But when I was first experimenting and just trying to figure this stuff out, I wanted reset under my direct control. So let's just take a look at the signals. I've got my oscilloscope set up here, to trace, let me just do it this way. So we've got three traces. The yellow trace is the clock signal. The blue trace is the computer out signal, the data out from the computer. And the purple trace is data in, so that's data coming back from the video board back to the computer. So you can see that the clock is currently idle at the low signal, whereas the data output from the computer is high. So let's just tell it to trigger on the clock signal, and then I'll do a simple operation. Just entering it here. Okay, and so here we can see a sort of protocol exchange between the computer and the video board. And even just at this level, if we look at the clock signal here, you can see a bunch of sets of signals. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. And those are essentially individual bytes that are being clocked by the computer. You can see that most of the data is here on the coming out from the computer, but there are some signals coming in. So let's just zoom in a little bit and see what's actually going on. So here we can see the actual the data going back and forth and the clocking. And in fact, if I zoom in, you can see that these are 1, 2, 3, 4, 5, 6, 7, 8. So these are 8 clock signals for 1 byte of data that's going in one direction or the other. And so clearly here on this first byte, this is data that's coming out from the computer. Because we can see some stuff going on here, and in fact, what this is doing is it reads a register from the video board, and then it writes it back. And so what we get, this first byte is the register set command, saying, okay, we're going to set to go for a particular register. So the first byte here is the command, and the second byte is the register that we want to set. So now we've set ourselves up with that register. And then the next byte here, this is the read command. So this is saying read the contents of that register. And as you can see, what happens then is that we keep the signal low. This is the data out from the computer signal stays low, but we still keep clocking. We send a bunch of clock signals, and that's clocking the data back from the video board. So here the video board sees the clock signals, and it uses those clock signals to coordinate sending back the data. So we've done the read. We said set up this register, that was 2 bytes, and then read it. And so that was 1 byte for the read command, and 1 byte coming back in the opposite direction is the data that's coming back from the video board. If we scroll along some more, we see here where I think this is the write command, and then this is the data to write back to that same register. So we read the value of the register, the program changed it, and then it sent it back. And what this command is actually doing is it's setting cursor mode. So it has to like read the current text set up, and then it has to set the bit that indicates that the cursor should be flashing, and then it writes it, and then it writes it back. So we get another 2 bytes, and that's the write this register, and here's the data to write. And then it does pretty much the same thing again. It has to do that for a couple of registers. I don't remember exactly what the setup is, but so we get 4 signals for this first data read and write, and then you can see that basically the same kind of pattern is going on over here for a different register. And so that's basically the way that things are working for SPI. The clock signal always comes from the computer. And sometimes it's clocking data that it's sending out, and sometimes it's clocking data that the serial device will send back. And so with basically these 3 signals, These are the sort of the one clock signal and then a data signal running in each direction. And then, as I said, the other thing that the computer is sending is the chip select, so that the device knows that it's the device that's being addressed. That's how we get serial input and output to an SPI device. And you're seeing also that this is an SPI mode 0 device, and so where the clock is idling at 0 and just goes up in order to indicate that that it's active. And if we zoom right in, you can see here's an example here. That we know that in mode 0, it's the rising edge of the clock is the point at which the data should be read. So there's the rising edge of the clock right there. And so the code ensures that the data that is to be written is already registered, is already being signaled. The data levels are already set, so that when that clock goes up, it's like, okay, that's what we want to be a 1. But the next rising edge here, we want that to be a 0, so it sets it down after the clock's been set. So that's what the signals look like on the wire. And maybe the next thing that would be useful to do is to look at the code that's actually producing those signals.
Let's take a look at the code that's making that signaling work. Because I want to show it to you because it's got a couple of really clever tricks in it. And when I say they're clever tricks, I need to point out that they're not my tricks, because the code I'm using is based on something from Jeff Lawton, who goes under the handle Dr. Jeffel on the 6502.org forum, and he put a lot of thought into this, and I want to show you some of the tricks that really helps this code run quickly. So just to start off with how the wiring is happening, so I'm using port B of this 6522, and the clock signal is on the first bit, so the lowest bit, bit 1. Or bit 0, depending on how you want to count. The MOSI signal is on bit 1 after that. The carriers, the chip select is on PB2. And the MISO signal is on PB7, so on the top bit, and which matters in ways that we'll see. So the ones that really, the MOSI doesn't really matter too much, and the chip select doesn't really matter. The ones that matter are clock on PB0 and MISO on PB7, and you'll see why that is. So here is the code to send a byte of data. And let me just take you through what this is doing. The first trick is this one. So clearly, sometimes you need to write a 1, and sometimes you need to write a 0. And we could be doing that using and and or instructions to set or reset the bit that's carrying the MISO signal. Or on the 65C02, which I'm using, you could be using TSB and TRB to manipulate that bit. But those are a little slow. So what this does instead is to pre-compute what the port should look like in those two conditions, either with MISO set or MOSI set, or with MOSI unset. And so it in LDY here, or in Y, we have a cache of what it should look like with the clock low but MOSI set. And meantime, in X, we have clock low and MOSI 0. Now, as I mentioned, I have the reset signal on here as well, so I actually have to set reset explicitly to make sure it stays high. So what this code can do then is, if it wants to send a 1, it does it saves an X, it transfers X to the port. And if it wants to, it's a 0. If it wants to send a 0, it sends X to the SPI port. And if it wants to send 1, it stores Y to the SPI port. And we don't have to manipulate those individual bits every time because we've pre-computed the values that we want, and that's much faster. Remember, of course, that these do not have the clock set. I'll come back to that one in a second. So that's the first trick that it uses, is to pre-compute the values so that you're not having to do any calculations on the fly. It's much faster to just store a value from a register into the port to do what we need. Okay, so what's the second trick? The second trick is just for keeping count of what we of how many bits we need to send. So obviously we need to send 8 bits for a byte, and so you might imagine that we have to count down from 7 to 0, or count up from 0 to 7, or 0 to 8, or something like that, in order to count whether we have sent all the bits yet. But Jeff's code actually uses another clever trick. So what we're going to be doing is we're using rotate left and shift left, actually mainly shift left, in order to peel the bits off. We want to send each bit from the top of the byte. The most significant bit gets sent first. And so the way we do that is in each loop we do a shift left, and that puts the top bit of the byte into the carry. And then we can look at the carry to determine whether we're sending a 1 or a 0. So if I shift the byte into the carry and the carry is clear, then I'm sending a 0. And if I shift a bit into the carry and the carry is clear, then I'm sending a 0. And if I shift a bit into the carry and that bit is 1, the carry is set, and so that's when I need to send a 1. So we're using that shift left in order to know in order to peel off the bits one by one and send them. But here's the trick. What Jeff's code does is he sets the carry and then rotates that in the first rotation into the byte. And so the point of this is we know that the marker at the bottom there's a 1-bit marker at the bottom of the byte that says where the byte ends. As we do ASLs, we're going to shift zeros into the byte at the bottom end. That's what ASL does. It puts the top bit into the carry and it shifts a 0 in. What that means is we know that there's always 1 bit at the top, or 1 bit at the bottom that was set. And when that bit that we set rotates into the carry, then the byte will be 0. That will mean 8 zeros have been shifted in through ASLs, and that will be the only time when the byte value in the accumulator is 0. We know it's the only time it's 0 because we've put a 1 in there with this set carry and then roll. And that means we don't have to count to see whether we've done all 8 bits. All 8 bits will be done when the accumulator is 0. So if we look at the send loop here, for instance, that's sending a 0, we store X on the port to send a 0. We increment the port to set the clock. We do the rotation. I haven't talked about the clock yet. I'll talk about that in a second. We do the rotation, and then we look to see whether the byte we're shifting is now 0. Because if it's 0, that means the sentinel bit has been shifted out into the carry, and that means that we're done. The only time we could possibly have the accumulator be 0 is when we've done all 8 bits. And so we don't have to maintain a counter. This inc SPI port that we've got here, both for sending the 1 and sending the 0, this explains why it is that we want the clock to be on bit 0 of the port. Because by doing an inc, we add 1, which means we set that bottom bit from 0 to 1. So it's just it's a very fast way of setting the clock high. So we know the clock is low because our pre-computed values have the clock low, and then the clock goes high, and that's when the data actually gets read by the serial device, and the clock will be set low again next time we go through this loop by either that STX or that STY. So these set the clock low, and then the next instruction sets the clock high, and that's how we're doing our clocking. What that means is we need to make sure that we leave the clock low at the end when we're done. But otherwise, using that ink is the fastest way to set the clock. And what's more, we know that we've already established the value on the port. Because remember what I said, that in mode 0, the data gets read on the rising edge. So we want to set the data first and then cause the clock edge to rise. So that use of a little sentinel bit, that's the second clever trick that Jeff's code uses. Let me show you the third trick. This is the cleverest of all, and it's in the data read. So the data read works very similarly. This LDA1 sets a sentinel bit so that we're going to use that to know when we've finished, when we've received the entire byte. But here's the trick that Jeff's code uses. See this here, that ink port to which raises the clock, sets the clock high. What it also does is to sense the top bit of the byte that's being read. And the reason is that any time the 6502 does a byte operation, it sets a flag, one of the status flags in the processor, to say whether or not that data was positive or negative. So it sets the N flag if it's negative. And in 2's complement representation of binary numbers, a negative number is signaled by something that has bit 7 set. So essentially this ink is doing output and input at the same time. It's doing output in the sense that it's adding 1, so it's setting the clock from 0 to 1. But it's also doing input because it will set the N flag in the processor according to bit 7. And bit 7, as I said, we have made into our MISO signal. It's the input to the data coming from the serial device and coming to the computer. So by doing that ink, we are both setting the clock, so telling the serial device that we want more data, and we're reading that data and storing it essentially in the N flag. So we can use a BPL here, branch if plus, to say if it's plus, that means the bit 7, that is the MISO bit, was 0, so we've read a 0. And if it's 1, then we know if it's negative, then we know we must have read a 1. There must have been a 1 in the high bit on the 6522 port, that is in bit 7, and that's the bit that we're reading from. And so then we can do the appropriate thing. We can either roll a 1 into our accumulator where we're keeping the value, or we shift a 0 in by using an ASL. But the trick in here is the fact that that ink is doing both the read and the write at the same time. And that really saves us an enormous amount of time, as you can imagine. It really sort of like adds up over the course of reading the data. So this is really, I think, pretty much the fastest way that you could possibly be reading this data in the 6502 or using the 6522. In my code, this is not the code that I actually use. In my code, I have this loop unrolled, but actually that loop unrolling saves you almost no time at all. It's actually, I suspect, better to have the code compactness and the readability that the loop gives you. And so I think I'm actually going to go back to doing that. Some of you will realize that the 6522 has a shift register built in, and so maybe we don't have to be reading these bits one at a time. Can't we use the shift register? Unfortunately, though, we need it's not compatible with mode 0, with that idea of reading the data on the rising edge. That's not how the 6522 shift register works, and that's why we have to do it by hand.
You can see here perhaps that I've already got a spot on the board where I'm going to put the 65 SPI. This is a sort of weird combination of a PLCC 44 to DIP adapter and then some headers so that I can wire wrap it. But before I'm able to put that in, I'm going to have to program the thing because the 65 SPI uses an ATF 1604 CPLD. So, and I'm going to have to program the CPLD, and in fact, to do that, I've got to build a programming cradle, which is probably what I'm going to talk about in the next video or two as I try to get that working.